I've been thinking about that conversation we had at the Scout and the Sentinel. ADHD and autism as cooperating specialists. The Scout pushing into the unknown, the Sentinel mapping it with precision. Together they create the pathfinder, the failsafe against tribal stagnation. That story made so much sense. It explained why those traits persisted, why they weren't just errors but strategies. So I started wondering about other traits. Strabismus. Lazy eye. Does it have a story like that?
That's a beautiful way to frame it. The Scout and the Sentinel, the ADHD side, dopamine-starved, constantly scanning, pushing into the unknown, and the autistic side with its high-gain sensory radar mapping everything with precision, together they created this pathfinder, the specialist who could not only find new environments but master them, the corrective mechanism that kept the tribe from following the leader off a cliff just because belonging felt good. That story works because those traits cooperate. They balance each other. The engine needs the anchor. The anchor needs the engine. And the genetic evidence backs it up: hybrid vigor, kin selection, the whole package. So when you look at strabismus, misaligned eyes, 2 to 4% of children, you'd think maybe there's a similar logic. Maybe having one eye slightly off gives you some advantage. Wider field of view. Better peripheral detection. Maybe it's another specialist adaptation, just one we haven't figured out yet. That's what you were looking for.
Is there?
It doesn't look like it. Or at least, that's not what the scientific literature thinks. Strabismus appears to be what it looks like: a developmental error, a glitch. The system for keeping two eyes aligned is incredibly complex: muscles, nerves, neural fusion circuits, proprioceptive feedback loops, 12 extraocular muscles, 6 per eye, firing in coordination, a visual cortex that takes two slightly different images and fuses them into one. Given all of that complexity, a 2 to 4% error rate is actually kind of remarkable. The system for binocular vision was worth the investment: depth perception for arboreal locomotion, hand-eye coordination for tool use, predation, the ability to judge distance precisely enough to strike, and those advantages outweighed the cost. The cost being strabismus. The 2 to 4% of humans whose eyes don't quite align. So that's the answer. Not a strategy. Just an acceptable error rate. The Scout and the Sentinel were the exception, not the rule. Most visible differences aren't adaptations. They're just what happens when a system that complex tries to run on biological hardware.
That answer felt too simple. Because strabismus isn't just a glitch, is it? It's also a marker.
Exactly. You've hit on something deeper. Strabismus isn't just a glitch, it's a marker. It signals that something else is going on in the developing nervous system. Sometimes nothing. Sometimes a lot. In some people, strabismus is just strabismus, an isolated mechanical issue. But in others, it's connected to something deeper. There's a gene called parade 4B that's been linked to both strabismus and schizophrenia. Not that strabismus causes schizophrenia, not that schizophrenia causes strabismus, but that the same underlying system, the same developmental pathways, influence both. Strabismus becomes this visible trace, this marker for a deeper system that you can't see directly. And once you start looking for that pattern, you see it everywhere. Traits that aren't adaptations in themselves, but are visible consequences of underlying genetic variation. The surface expression of a system that never compiles cleanly. The Scout and the Sentinel led us here to a whole different way of seeing.
Give me other examples. What else is a marker like that?
Epicanthal folds, the skin fold over the inner corner of the eye. It's a normal trait in many populations, a neutral variant that doesn't do anything in particular. But in European contexts, epicanthal folds became a marker for Down syndrome. Not because the fold itself is a problem, but because the same chromosomal variation that causes Down syndrome also affects facial development, and the fold is visible in a way that the underlying variation is not. Simian crease, the single line across the palm instead of the usual two, shows up in about 1 in 30 people as a normal variant. But when it shows up with other signs, it raises questions. Another marker for Down syndrome. Another trace of deeper variation. Café-au-lait spots, those flat light brown birthmarks. Most people have a few. More than 5 or 6 is a marker for neurofibromatosis, a genetic condition that affects nerve tissue. The spots themselves are harmless. They're just visible. They're the surface expression of a system that can't be perfect every time. None of these traits are adaptations. They're not the scout or the sentinel. They're just markers. And markers point to something about how genomes actually work. The scout and the sentinel were the door. This is what's on the other side.
Pleiotropy.
One gene, multiple effects. The same gene that guides neuronal migration also influences eye alignment, also influences palate shape, also influences a dozen other things you'd never connect. Change one thing and 10 unrelated things change with it. That's why strabismus isn't just an eye problem, it's a marker, a visible trace of a deeper system, the system for building a nervous system, the system for building a human. Evolution doesn't optimize each trait independently because it can't. The genome is a web. Pull one thread and everything moves. Selection works on overall fitness, on what works well enough in enough bodies in enough contexts for long enough to get passed down. Pleiotropy means that when you select for one thing, you get all the other things that gene does too, good or bad, relevant or irrelevant. You get the whole package. So strabismus persists not because it's useful but because the genes that cause it sometimes are. Because those genes are doing something else that is useful. The eye misalignment is collateral damage from a system that's doing something more important. That's the lesson from the scout and the sentinel. Traits that look like deficits can be strategies. But sometimes traits that look like deficits are just the price of complexity.
And then there's the viral code.
Endogenous retroviruses, leftover insertions from ancient infections, retroviruses that inserted themselves into our ancestors' DNA millions of years ago. Most of that viral code is dead now, broken, degraded, but some of it got repurposed. There's a retrovirus that infected our ancestors 50 million years ago that is now essential for building the placenta. The system got hacked, the hack became a feature, and the feature became a dependency. This is how genomes work, they accumulate, they never start over, there's no clean install. Every new adaptation is built on top of whatever was already there, and if it works well enough it stays, and if it breaks something evolution works around it. Patches on patches. Features that were critical for our fish ancestors now repurposed for jaws and ears. The old pathways are still there, still active, still capable of producing bugs when something goes slightly wrong. Endogenous retroviruses, dead code that became critical, that's not exceptional, that's normal. That's how you get a system that's been running for 3 billion years without ever being rebooted.
So the genome is legacy code.
Technical debt, every developer knows it. The quick fix that becomes permanent, the patch that gets another patch, the code you're afraid to touch because you don't know what will break, the function that does 3 unrelated things because no one had time to refactor it, the documentation that was never written, the original developer who left the company 10 years ago, the system that still runs somehow but no one fully understands why. The genome is technical debt accumulated for 3 billion years. No one ever refactored it. No one ever will. The hardware hasn't been upgraded in 300,000 years, and yet the system boots most of the time. It runs. It produces language, culture, mathematics, consciousness. It does all of that with a codebase that is a mess. That's not a criticism, that's a description. The scout and the sentinel are features that worked so well they got kept. Strabismus is a bug, or rather it's a visible symptom of a system that can't compile cleanly every time. The same system that gives us depth perception and tool use and the ability to read and write gives us strabismus. You don't get the one without the risk of the other. Complexity has a cost.
So what do we call disorder? Schizophrenia. Strabismus. Infertility. The scout and the sentinel sometimes get called disorders too. Are these design flaws?
They're not design flaws in the sense of failures of optimization, they're the cost of a system complex enough to produce everything we value. Schizophrenia affects about 1% of people. Strabismus, 2 to 4%. Infertility, 10 to 15%. These aren't signs that the system is broken. They're signs that the system is doing something incredibly difficult. We pathologize the visible errors, call them disorders, conditions, deficits, treat them as if they're separate from the system, as if there's a platonic ideal of a correctly compiled human and these are the ones that came out wrong. But there is no clean compile. There never was. The standards are set to good enough for the species to continue, and everything else, every quirk, every vulnerability, every trait that works well enough in enough bodies, persists. The scout and the sentinel persisted not because they were errors but because they were strategies, specialized functions that helped the tribe survive. That's one category. Strabismus persisted for a different reason, not because it was useful but because it was the cost of a system that was useful. The acceptable error rate. The visible marker of deeper complexity. Both are real. Both are part of the same system.
So the question isn't what's wrong?
The question is, what is this system actually doing? What constraints is it operating under? What does it need to keep running? What worked well enough in enough bodies in enough contexts for long enough to get passed down? That's the evolutionary biologist's question. That's the legacy code maintainer's question. That's the question you've been asking all along, starting with the scout and the sentinel, moving through strabismus, through markers, through pleiotropy, through viral code, through technical debt. Not what's broken, but what is this? Because when you ask what is this, instead of what's wrong with it, you stop treating traits like errors and start seeing them as what they are, expressions of a system that has been running for 3 billion years, accumulating patches, making trade-offs, accepting error rates, and somehow, against all odds, still booting up every morning. The scout and the sentinel are part of that system. Strabismus is part of that system. The viral code is part of that system. The technical debt is part of that system. The whole messy, patched, never refactored, somehow still running system. That's what we're looking at. That's what we've been looking at the whole time.
That's where the scout and the sentinel were trying to go.
That's exactly it. The scout and the sentinel were never just about ADHD and autism. They were the entry point. They were the door. They showed us that traits we call disorders can be strategies, can be adaptations, can be the thing that keeps the tribe from following the leader off a cliff. And once you see that, you start asking the question about everything. About strabismus. About markers. About the whole genome. About what this system is actually doing. The scout pushes into the unknown. The sentinel maps it. Together they find the path. That's what this whole conversation has been. That's what the audit log is. Not what's wrong, but what is this? And once you start asking that question, you can't stop. Because the answer is always more interesting than the assumption that something is broken.